Welcome to this video about using the FFT, the fast Fourier transform, for friction ridge enhancement. To get the most from this filter, you need to understand some fundamentals about FFTs, so this video will be a little longer than most of our videos, but it will be focused on latent print enhancements. The two main applications of the FFT for friction ridges are to remove background patterns if they are repeating, and to separate overlapping prints as long as the ridge flows are in different directions. If you have an image that might benefit from the FFT filter, you first need to make sure that it's 8-bit grayscale. To convert a color image to 8-bit, you need to use either the color to grayscale function or the color sliders. Those functions are covered in other videos. So when you click on the FFT button in the Enhanced interface, you will see the frequency spectrum representation of that image in the FFT interface that appears. This is a close-up of the interface that you see after you click the FFT button. The data displayed in the FFT interface, right here, represents the Fourier or the frequency spectrum of the spatial image that you're working on. Here are some features of this data. For example, Q1 and Q3 are mirror images of each other. Q2 and Q4 are mirror images. The data represent the frequencies that are present in the spatial image. The very middle of this data represents the average grayscale intensity of the spatial image. As you move away from the center, the data represented gets higher and higher frequency. So in this middle part, it's still fairly low frequency, and when you add masks in here, you're definitely going to notice it. As you move further away, it's higher frequencies that you're masking out, and those masks will be less noticeable. So here are three spatial images. These are sine waves of varying frequencies, starting lower and getting higher. And here are the corresponding Fourier spectra. Each spectrum has two bright spots, and they correspond to the frequency of the sine wave. As the frequency gets higher, the two bright spots move further apart. In these images, you can see that the location of the bright spots is determined by the angle of the sine waves. So as the sine wave rotates, so do the bright spots in the spectra. In this slide, I'm just showing the difference between what you're going to see in the spectra for a sine wave, which gives you the two dots, as we saw before, versus stripes, black and white stripes. You get the same two dots that are present for the sine wave, but you also get many more repeated dots along the same line. This is called ringing, and if you have something that's in between a sine wave and a stripe, so just a little bit blurry edges, you'll still get ringing, but it won't extend into the higher frequencies. The sharper the edges, the more ringing you're going to see in the spectrum. Here are some patterns and their corresponding spectra. I'm just showing these examples so that when you have a repeating pattern to remove, you'll know what to look for in the frequency spectrum. In this slide, I'm showing the spectra for a couple of fabrics that I scanned. In this second one here, the weave is not actually lined up with the edge of the image, so the pattern is a little bit at an angle, and you can see this in the frequency spectrum. Here you can see the spectra for two fingerprint images. You'll see this typical donut shape. You can kind of think of fingerprints as stripes or sine waves that rotate 360 degrees, and that's what gives you this donut shape, because most of the angles are covered by the stripes or sine waves. Normally when you're adding masks, if you can avoid this donut for the fingerprint, that's recommended. The size of the donut you see in the spectrum display depends on the image resolution. So for a 300 ppi image, the donut shape looks fairly large. 750 ppi, smaller, and 1500 ppi, it's even smaller. Just so you know what to expect when you first open the FFT interface. You may notice that these aren't full donuts, that there's gaps in the horizontal area. And that's just because with these fingerprint patterns, there aren't really any horizontal ridges. Very often, when you look at the spectrum, you're going to see a vertical and a horizontal line that intersect the middle of the spectrum. These are just artifacts from the image padding we have to do to generate the spectrum data. They're less prominent if we don't have to do padding. So if your image is one of these sizes, a 512 by 512 or a 1024 by 1024, it's just an artifact. So usually there's no need to mask these lines. Here you see a comparison of the same fingerprint that I cropped twice. Once I cropped with an irregular size, and the second one I cropped with the 512 by 512, and you can see that the horizontal and vertical cross is less noticeable on this right side. So here we are back at this screen grab I showed at the start of the video. Now you may be able to understand some of the features you see in the spectrum. You can sort of see the donut from the fingerprint right here. You see the dots caused by the stripes that are in this direction right here, and you can see the cross artifact from the image padding. So let's focus on the tools you have in the FFT interface. Because of the mirroring effect, if you check this, whenever you add one dot, we automatically add the corresponding dot. Here is where you pick the filter mask that you're going to apply. You can either apply a circle or a line. This is where you select the pen size of the mask. The default is 10. When you add a mask, if it's too big, you can just say undo last draw and then make this pen size smaller and try adding it again. This is where you undo last draw, and you can also undo all draw. Like with annotate in the main interface, there are three modes. There's draw mode, where you're adding masks. Edit mode, where you can edit a mask that's already there, and pan mode. Here is where you select the way you see this frequency spectrum. You either see it as grayscale, as we see here, or you see it in black and white, where you set the threshold that's applied. I find you need to go back and forth between these two modes to find all the bright spots in the data. Sometimes masks can be huge, and you may want to save them for future use or just for your records, and you click Save Mask if you want to do that. If you want to load a mask that you saved, this is where you do that. Click OK if you want to apply your masks, and exit this GUI, and cancel if you just want to get out of the GUI. So as you add masks, the spatial image will update. So the math for this inverse Fourier transform is fairly intense. So it may take a while if your image is large or if your computer is slow. So just as you add the masks, just wait for the image to update and then continue to add more. That way you can keep an eye on what's going on and undo anything that didn't improve the contrast of your print. So let's go back to this example and just notice the spatial image here with the stripes. And in the next slide you're going to see what the stripes look like after some masks have been applied to the bright spots here in the frequency spectrum. So you can see that the stripes are suppressed. The masks are displayed in the frequency domain as red, and that's just so that they're very visible on the grayscale background. Here's another example of a fingerprint on a pattern background. In this example, I just want to show the effect that different sizes of masks have. So here you can see the donut shape of the fingerprint, and here you see the bright spots from the polka dots. What I did is loaded the same image on both sides. On the left side here, the masks I used to mask out the polka dots are fairly big, and this is what the result looks like. On the right side, I used smaller masks, and this is what the result looks like. And here they are side by side. As you can see, the larger masks actually degraded the print more than the smaller masks did. The best advice I can give is to use the smallest mask possible. Now I'll do a demo so you can see how this works. So I've opened up an image here on the left that's a fingerprint over fabric. It's already 8-bit, so I don't need to convert it to 8-bit. Click on FFT. Now with this interface you can zoom in and out using your mouse roller, the way we've allowed in the main images. If I want to start adding masks, go to draw mode. I'm going to add circles I'll try with the default, and the size is pretty good. So then I just start adding them. And as you can see, the image updates every time I add a mask. And every time I add a mask, it adds the mirror mask automatically. Now, if I wanted to look at the frequency spectrum in black and white, just go to black and white and then just move the threshold up and down. It's another way to look for spikes. And you can still draw when it's in black and white. So I have worked on this mask before starting to record. I'll just load the mask that I generated before. I'll just open the one that I did. As you can see, I added quite a few dots. And this is the result right here. And I'll just click apply. So it's a lot easier to see the ridges in the final image. I'll just click undo, redo, so you can see the difference. The other way the FFT can help is with overlapping friction ridges. It can help wherever the ridge flows are in different directions, and you will usually have to work on small sections one at a time. In this slide, you can see what the spectrum looks like for different ridge flow directions. In the delta region, all directions are present, so the spectrum is back to that typical donut shape. But in areas where the ridge flow is just mainly in one direction, you'll see just two major spots in the frequency data. In this section that's outlined in red, the left print ridges are horizontal and the right print ridges are vertical/diagonal. I've placed these two masks here to suppress the vertical/diagonal ridges, and you can see the result. They're blurred out and the horizontal ridges remain. In this section, I have placed the masks to also suppress the more diagonal, in this case, slightly more diagonal/vertical ridges, and to keep the ridges that are in this direction. Here's the final image where you can see that the ridges on the left print are emphasized and the ridges from the right print are suppressed. Here's another example of overlapping prints. And in this region here, I have suppressed the horizontal-ish ridges from the background. And it did a pretty nice job. It seems to me that the higher resolution your image, the cleaner you can get the final image. So just keep that in mind. In this example of overlapping prints, I'm going to suppress the left print ridges. So to do this, I need to select a region and use polygon. I'll just operate on this part first. Click FFT. Now you can see that there are 4 main bright spots. I want to suppress the spots that are horizontal and a little bit facing this direction. So just draw mode, and I'll try with the default size mask. It's a little bit big, but it's not too bad to suppress the horizontal-ish prints. If I want to undo, I can just undo all draw now because I only drew the 2 of them. And I can try a smaller. So basically you just need to play around with it and see what gives a nice result. And you can add extra ones and just click OK when it looks all right. And the other thing you can do at this point, if you want the background to look more similar to the background you see here, you can go to levels and just brighten up the background a little bit. And it looks okay, so click apply. So that's how you can use the FFT to help separate overlapping prints. Thank you for watching. If you have any comments or questions, feel free to reach out to me.